host rights to Sri Samal sir. Now, YouTube stream started, sir.
Yeah, started. Okay, thank you. Amit, when you want to start?
Yeah, so I want to start the talk at 11, sharp at 11. So just wait for 1 minute and then I will start the opening sessions.
So as per agenda, you can go.
Yeah. Okay, so let me start. Good morning, everyone, to the invited speakers, our VC sir, Pro VC sir, and also to all the participants and the panelists. So this is a one-day national symposium on high energy physics organized from our Department of Physics at SRM University, AP. And so the plan is we will have three pedagogical talks on three different directions in the field of high energy physics. So the first talk will be given by Padmashri Professor Rohini Godbole from IISc Bangalore. And the afternoon session, we have first talk on dark matter physics by Professor Vasudev Dasgupta. And at 4 p.m., we will have a talk by Professor Bala Iyer. So he will be giving a talk on gravitational waves. That is also one of the very interesting and I would say very prominent topic in recent days in high energy physics. So without any delay, may I ask Professor B.S. Rao, Vice Chancellor of SRM University, to welcome the participants and the speakers.
Thank you, Professor Amit. Distinguished speakers, Professor Rohini Godbole and Professor Vasudev Dasgupta, our beloved Pro Vice Chancellor, Professor Narayan Rao Garu, our Associate Dean, Professor Durga Rao, Head of the Department of Physics, Professor Ranjit, and other distinguished participants, students and faculty. At the very outset, let me welcome you all to this one-day National Symposium on High Energy Physics organized by our Department of Physics. I think I do not have to tell physicists the revolution the particle physics area has created in the last century, be it in the physics or in the energy studies. Particle physics has revolutionized the entire energy sector. Quantum theory and various other applications, standard model, and many other things that you people are going to talk about. I'm very happy to welcome you all once again to this National Symposium, and I would like to congratulate and compliment the physics department, young faculty members who have taken this initiative. This university was established in the year 2016 under Private University Act. And we are now into our fourth year, having started our classworks for at least 3 disciplines in the School of Engineering. computer science engineering, mechanical engineering, and electronics communication engineering. The first batch is going to graduate with almost 92% of placements and a good number of students of the first batch going for higher education in well-reputed institutions. In the subsequent year, we have started our School of Sciences, offering bachelor's programs in physics, chemistry, mathematics, biology, and School of Liberal Arts, offering programs in BA, psychology, BA history, BA in English and journalism, and School of Management offering BBA programs in the same year. Now, all these students are going to graduate. The first batch is going to graduate this year. And we are very happy for having established very good departments in the sciences areas. And this university can proudly claim that we could be one of the very few private universities who have made such accomplishments in the area of research, be it publications in well-reputed journals, be it patents, or be it projects. Today we have over 100 and odd PhD students. In a matter of 2 to 3 years, although university started 4 years, by the time we established laboratories, it could have taken easily 1 year for faculty joining. So in a matter of 2.5 years, our faculty, of course, 100% PhDs with international exposure, have made all these things possible. We have now become a research-intensive university in our formative years. And we are also laying very good emphasis on liberal arts and integration of liberal arts with technology and science programs. And our School of Management also has started MBA in Banking and Finance and MBA in Business Analytics. Today, we have around 3,200 students enrolled. By next year, we are going to touch around 4,500 students. And our aim is to have 200 PhD students. All these will help us in making a research intensive new age university by next 1 or 2 years. We have created the state-of-the-art infrastructure, be it physical or be it academic, and with our faculty support, we will be able to accomplish our vision to become a world-class university. With these words, I would once again welcome all the participants, and I would like to express our gratitude to Professor Rohini Godbole, Professor Basudev Dasgupta, and Professor Bala Iyer for taking time out of their busy schedule to participate in this national symposium. I'm sure the deliberations will certainly help all the participants, because these distinguished speakers are going to show us the paths for the future research in particle physics and various applications in particle physics. I'm sure all of you are going to be immensely benefited through the deliberations of this symposium. Congratulations to the organizing team, and I wish you all the best. Thank you.
Thank you, sir. Thank you for the kind words. May I now request Professor D. Narayana Rao, our Pro VC sir, to say a few words.
Our distinguished Vice Chancellor, Professor V.S. Rao Garu, highly reputed scientists of this country and who are the invited speakers here, Professor Rohini Godbole from the most prestigious institute, IISc of Bangalore. Am I lost?
No, we can hear.
You're audible.
No, yeah, it's audible, sir.
No, I'm
We can hear
reconnecting.
you. We can hear you.
Oh,
You are connected, Narayana, sir.
We can hear you, sir. Please go ahead.
We can hear you and see you, sir.
okay, fine. Professor Das Gupta, Professor Bala Iyer, the Dean, Professor Durga Rao, the head of the Department of Physics, Professor Ranjit Thapa, Dr. Amit, and other faculty members, the participants. I have great pleasure in associating myself with the National Symposium on High Energy Physics being organized by the Department of Physics. I used to contact Professor Bala Iyer, who will join this afternoon, while inviting Kip Thorne and Bala Iyer for a prestigious meeting in the year 2017. Later, of course, Kip Thorne got the Nobel Prize. Thus, I have contacts with Bala Iyer at that time. As the Vice Chancellor mentioned, the university is established in July 2017 as a multi-stream research intensive university. Presently, we have about 150 highly passionate and committed faculty members, including 4 DST Inspire Fellows and 1 DBT Ramalingasamy Fellow. All our faculty members have international experience and international exposure. They obtained their PhD degrees from highly reputed universities and institutions in India and abroad. As I said, most of our faculty members are research hungry and passionate, and they are carrying out research areas in frontline and emerging areas of science and technology. In the last 2 years, our faculty members have published 400 papers in reputed journals, including Nature, Nature Communications, Nature Microbiology, PNAS, and others. 20 patents have been published by the faculty members and students of this university in the last couple of years. Our faculty members obtain projects from DST, DBT, DRDO, the Board of Research in Nuclear Science, BRNS, including the prestigious DBT Wellcome Trust Award. We have established a few research centers, one of them being SRM Amar Raja Center for Energy Storage Devices, in association with the leading battery manufacturer in the country, namely Amar Raja Batteries Limited. The objectives are fast charging of lithium-ion electrodes, development of cost-effective materials for lithium-ion batteries, 3D printing of electrodes for lithium-ion batteries, and to work beyond lithium, namely sodium and others. The center is established here, as I said, in association with the industry, Amar Raja Batteries. We have established Center for Weather Forecast in association with India Meteorological Department, providing weather forecast for the entire state of Andhra Pradesh. And we have also taken up a few special projects which are worth mentioning, namely hydrogen-powered fuel cell-based train in association with Integral Coach Factory of the Ministry of Railways. India will be the second country to demonstrate a fuel cell-based hydrogen-powered train. We are also developing gold foam for jewelry applications in collaboration with Tanishq Jewelers, and 3D printing of gold jewelry, again in association with Tanishq Jewelers. Now we are taking up 3D printing of bio implants, metal additive manufacturing for strategic applications, etc. Thus, this university, though research-wise it's only 2 year old, we are happy that our faculty members are performing beyond our expectations, and with the support of the management, the vice chancellor, and the deans, I'm glad to inform that this university will be one of the well-known universities in the country in the next 5 years. Of course, with the support and guidance from the reputed scientists like Rohini Godbole, Professor Das Gupta, Bala Iyer, and others. I thank the organizers for giving me an opportunity to share my thoughts on research activities of the university. Thank you, one and all.
Thank you, Professor Narayana Rao, for
Yeah.
the kind words. So now we will start the main event. So it's my privilege to introduce Professor Rohini Godbole. She is a distinguished professor at the Center for High Energy Physics in the Indian Institute of Science in Bangalore. So she is working for last 3 decades almost in the field of particle physics, exploring different theoretical aspects of standard model of particle physics, beyond standard model of particle physics, for example, supersymmetric theories, dark matter physics, collider physics, neutrino physics. So she has, I mean, as I said, she is one of the role model in our field of particle physics, especially for Indian communities. And she has published almost 200 scientific articles in different reputed journals. Let me give you just very brief idea of her education. So she did masters at IIT Mumbai, and then PhD from Stony Brook at USA. And then she joined Tata Institute of Fundamental Research as a visiting fellow. And then later she was working for a long time at the Department of Physics, Mumbai University. And from, I guess, 1995, she moved to IISc Bangalore. And since then, she is there as a senior distinguished professor. She is also fellow of all 3 academies of science in India. I would like to mention a couple of things before her, which is very noteworthy. First is that she has also co-authored 2 books. One is in the context of supersymmetry. It's called Theory and Phenomenology of Particles, which and every particle physics has this book. It's a very nice book. And very recently, in 2008, she published co-authored a book called Lilabati's Daughter. So this is Women Scientists in India. It is one of the highly, strongly recommended book for everyone, all of us. And now regarding the awards, she has got, I mean, numerous awards from different sectors, but 2 of them are very noteworthy. In 2019, Government of India has given her the prestigious Padma Shri Award for her contribution in Indian science and technology. And very recently, this year, 2021, she got the National Order of Merit from the French scientific community. This is also among the highest distinctions bestowed by the French government to any foreign scientist. So we are very, very happy and to have Professor Godbole with us. Thank you, madam, for accepting our invitation. So please start your seminar. Thank you.
Thank you very much. The Vice Chancellor of SRM University, Professor V.S. Rao, the Pro Vice Chancellor, Professor Narayan Rao, the Dean, Professor Durga Rao, the Head of the Department, Dr. Thapar, and my young friend Amit, who not so long ago was a member of our department at the Center for High Energy Physics. I must really like to thank you for inviting me to talk to your students. I should also congratulate Professor V.S. Rao and Professor Narayan Rao for the wonderful news about SRM University that they bring to us. And I hope that the SRM University becomes the role model for the research universities that the new education policy is looking forward to.
Yeah.
And if there is anything in the processes in which way I could be of any help to this exercise, I would be quite happy to add my 2 bits worth, and wish you all the well for the university's future. So, having said these things, let's come back now to business, as it were. And the business is to tell you a little bit about the status of particle physics. So, let me begin by sharing my screen. So, let us just hope that that works, because that's always for me an adventure. Okay, so let's go here. Share screen.
Yeah.
And can
we can
people see my
Yeah,
screen?
we can
Okay.
see. Yes.
Okay, very good. So, again, as I said, thank you very much for inviting me to give this talk. And I discussed with Amit what I should be talking about, and he liked this particular title, so I have chosen it. It's Status of Particle Physics in the Light of Physics Nobel Prizes of 2013 and 2015. I should, in principle, perhaps have added the light of the Nobel Prize also for the gravitational waves.
Good thought.
But since there is a special talk dedicated to that, I decided not to add that in this title. So there is a reason why I have introduced these 2 Nobel Prizes, and I will try to tell you why. So first, I will tell you very briefly about the 2 Nobel Prizes in physics of 2013 and 2015. And I will tell a few things which you read even in popular science literature about the hurrah for the standard model of particle physics. And then somewhere I will give you a summary of the life story of the standard model, so that one appreciates what does this hurrah really mean. And then the most important question or important issue as to where does the subject go further. So let's see how we go with this story. So the Nobel Prize of 2013 was for the discovery of the Higgs boson, and this discovery was the final piece of information that was necessary to prove that the currently accepted description of fundamental particles and interactions among them, which we call as the standard model, it's called model but it's theory. So this is the, how should I say, splitting the hair that the theorists are always physicists would like to split. Something which is a model may actually sometimes be changed, may sometimes be get corrected, but when we say Newton's theory of gravitation, then that's absolute. Or Einstein's theory of general relativity, that's absolute. So standard model actually now has reached that stage of being a theory, but we call it a model. And the second Nobel Prize was Nobel Prize of 2015, and this was the discovery that the neutrinos actually change their character while traveling through vacuum. And it actually gives proof that neutrinos are not massless, but they have mass. And that, which I will explain this, but I am basically quoting from the citation of the Nobel Prize, that this non-zero mass of the neutrinos actually implied that there must exist physics, either particles or interactions, beyond the standard model, and this is what we call BSM Physics. So you see already, the Nobel Prize of 2013 proved to us that we have reached or arrived at the correct description of the fundamental particles and interactions among them. And the Nobel Prize of 2015 told us there is still further to go. There is still physics, particles and interactions beyond this standard model. So that's really the reason why I have said that I want to talk about status of particle physics in the light of these two Nobel Prizes. So I will now read the citation of the Nobel Prize of 2013. It says the Nobel Prize in Physics in 2013 is awarded jointly to Francois Anglais and Peter W. Higgs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of the mass of the subatomic particles, and this is the second part of the clause, equally important, and which recently was confirmed through the discovery of the predicted fundamental particle, namely the Higgs boson, by the ATLAS and CMS experiment at the CERN's Large Hadron Collider. There are three parts to this citation. One thing is that it was given for the mechanism. It was given for pure theoretical considerations, pure theoretical work. And this was like the triumph of pure theory. But the Nobel Prize was given only when the prediction of this theory, prediction of this mechanism was confirmed by the discovery of the Higgs boson, and this confirmation of the theoretical speculation by experiments required, in fact, participation of the experimental groups at different institutes, different universities all across the world, but also in particular from all over India, and also a host of theorists from all over India. All these physicists, experimentalists and theorists have been involved right from the beginning in this exercise, which is why the entire particle physics community at that time, on that day in 2012, 4th July, when the Higgs boson discovery was announced, felt like it had got the Nobel Prize. Nobel Prize was of course given to the Peter W. Higgs and Francois Anglais, who originally put forward the idea. Remember, the Higgs postulate was actually 1961. Its use was in 1967 in theory. Machine design, which finally found the Higgs boson, started in 1984. Machine building started in 1998, and the experiments gave the result in 2012. And now from 2012 to 2021, in 10 years, we have had very wonderful confirmation of the properties of the Higgs boson. What is the point I want to make here? The point I want to make here is that the high energy physics experiments need a lot of lead time to plan, not just because they are huge and costly, but also because they are very complex. And the money and the cost and the work, all of it gets spread over many decades. And not just that, but it requires the cutting edge technology. So it helps also development of cutting edge technology. Just to give you an example, the World Wide Web was actually invented by high energy physicists because they wanted to share experimental data. And to be honest, I can't even imagine what our life would have been like without the web in the last 1 year and few months of the COVID stricken days, So what I'm trying to tell you that there are many, many dimensions to a high energy physics experiment, and that we could do well to keep in mind. The Nobel Prize in Physics 2015 was given by, again I am quoting the citation, it was given to Takaki Kajita and Arthur MacDonald, one from Japan and one from Canada. Again, you see the globality of particle physics as a subject. It does not belong to one country. It does not belong to one lab. It belongs to the whole world. And this was given for the discovery of neutrino oscillations, which shows that neutrinos have mass. So this is a very nice cartoon that was made by my friend for a particular experiment, and I'm just taking the liberty of producing it. And what these experiments really proved, that a neutrino of the electron type suddenly, which came from the sun, actually when the experimentalists were observing it from Earth, they suddenly see it convert itself, change its character, and go from neutrino of the electron type to neutrino of the tau type. India actually has been involved in neutrino experiments in a big way. It's very nice to know at this point that one of the first atmospheric neutrino detection was done in Indian Kolar goldfield mines experiments, KGF it is called. Now KGF is closed, but now Indian scientists are planning to build Indian Neutrino Observatory, INO, to join the neutrino game. Now, one point I want to just tell you, that among the Nobel Prizes that have been awarded for physics till date, out of the year, out of these, in 24 of the years, they were given for experimental discoveries or theoretical breakthroughs that have contributed to the standard model to 47 scientists. First in 1936 and the most recent in the 2013. So 2013 in some sense was the last Nobel for the standard model, and 2015 is the first Nobel for the physics beyond standard model. So that kind of tells you that in particle physics, the game is the king is dead, long live the king. That's what the story is, which I want to bring to you. Also, this tells you that the 20th century has been century of particle physics and century of the standard model. So right now, particle physics actually finds itself in an extremely peculiar place. And I don't know how many of you read literature, but there is a very famous book called A Tale of Two Cities, written by a very famous author called Charles Dickens. And apologies to him as well as to Shri Rup Raichaudhary from TIFR, from whom I have stole the idea. But the first few lines of that novel start like this. It's the best of the times, it's the worst of the times. It's the epoch of belief, it's the epoch of incredulity. It's the season of light, it's the season of darkness. Of course, the author is referring to French Revolution, but we don't have to worry about it because this describes precisely the situation in particle physics right now. It's the best of the times because we have found the Higgs boson. It's the best of the times because we have confirmed the predictions of the standard model. And why is it the worst of the times? That I'm going to come to the next slide. It is the epoch of belief in standard model, and it is the epoch of incredulity that we haven't found anything beyond it. And in a lighter note, it is the season of light because the Higgs boson was indeed found in its decay into two quanta of light, 2 photons. That was the first signature of the Higgs boson. And it is the season of darkness because it seems to be now the coming decades seem to be the decades of the study of dark matter, about which you are going to hear quite a bit more in the talk by my another young friend, Basudev Dasgupta. So, we have everything before us and we have nothing before us. Look, I have really produced the 5 lines from the book as it comes, and that describes to me exactly what the standard model is at the present, what particle physicists feel at present. We have found a standard model Higgs boson. We have proved the standard model, but we have no glimmer at the Large Hadron Collider of the type of beyond standard model physics that the observed Higgs properties promise. The non-zero masses of the neutrinos imply some BSM physics, but the Higgs properties that we see don't imply non-zero neutrino masses. So there are more things yet to discover, and in all this journey, colliders have helped a lot for this progress in the world of particle physics. So, we particle physicists need, all of us can be justified when we feel a bit like Lord Kelvin. I don't know how many of you remember the name of Lord Kelvin, but when Kelvin scale of temperatures is something we all study, whether we are physicists, chemists, or whether we are whether we are engineers, we study thermodynamics, and Kelvin temperature scale is something we do all know. And Lord Kelvin, at the end of 18th century, had in fact said that there is nothing new to be discovered in physics now. All that remains is more and more precise measurements. That's what he thought. But then there was one cloud on the horizon, and that was the understanding of the black body radiation. And all of us know that ushered in the area of quantum physics, quantum mechanics, and even today it moves us on not just to particle physics but quantum information. It takes us to the area of laser technology and a whole lot of other things. So when we thought that everything was over, classical physics was complete, we found a completely new way of going forward. So mere mortals today can actually feel like this, that all that remains now is perhaps more and more precise measurements of the Higgs and the other heavy quark called top quark, and also properties of an object called B mesons. So do we have to do more and more precise measurements, or do we have to go to higher and higher energies, or is there a third path? And that is the story that I want to bring to you. So the elementary particle physics, according to the world of elementary particle physics, the accepted worldview is, and you can go to Wikipedia, you will find it in 5 minutes, that the fundamental particles are the quarks, the leptons, and there exist 4 fundamental interactions among them, out of which the standard model deals with only 3, that is weak, electromagnetic, and strong. And the interactions, the forces among these quarks and leptons are caused by exchanges of particles which we call them force carriers, and these force carriers are called bosons, the photon, the WZ boson, and the gluon, and the omnipresent Higgs boson, which was postulated by Higgs and Anglais for solving some theoretical problems that the mathematical description of these interactions would have had. And thus this is the periodic table of particle physics, if you like. But then you could say, okay, so this is a fact of interest to maybe 10,000 particle physics physicists working all over the world. Why should I be listening to it? Why should this be important and interesting to me? So the important thing is, this is not just of interest to particle physicists, but the laws of particle physics, which you have found to be functioning on distant scales of Fermis and smaller, seem to be of relevance and capable of understanding things that happen on cosmological time scale. And what do you mean by cosmological time scales? You mean at the beginning of the universe, and at the astronomical distance scales, which is millions of megaparsecs and above. There are other inputs that are required, but the knowledge of particle physics is required and is capable of providing answers to the questions such as, how was everything formed? How did the nucleons form? What existed at the beginning of the universe? How did matter come into being? Can we explain the relative abundance of the different elements in the universe? In the star, how did the stars form? How did the galaxies form? Why do galaxies and stars contain different material, different elements in the proportions that they do? Believe it or not, but these questions, which involve immense distances and immense time scales, as I told you, cosmological time scales and astronomical distances, these questions is the distance that light travels in 1 year. And just to tell you, it takes 8 minutes for light from sun to reach us. So that should give you an idea what is the distance that light can travel in 1 year. So we are just beginning to realize, and the universe itself is, as I said, it's millions of megaparsecs. Now the periodic table of fundamental particles and their interactions is now finalized. This is what happened on, I would say, in the decades beginning from 19 1897 when electron was discovered by Thomson. And the story ended in, particularly this story that I am showing you here, ended in 1995 when the top quark was discovered. And when I say that, periodic table has been filled, we actually know the masses of all the particles. We know their electric charges. They have been measured accurately. And one of the important things that all of them have spin in units of the fundamental h cross h over 2 pi. They have all spin half. They were divided into two classes, leptons and quarks. And for explaining things than the matter around us, all we need is this first two lines. Two up quarks and one down quark makes a proton. Two down quarks and one up quark makes a neutron. Protons and neutrons make a nucleus. Nucleus and electrons make atoms. And when the nuclei disintegrate or nuclear reactions happen inside the sun, at that time neutrinos are emitted, and this is really the matter that is around us. But all these extra particles are actually produced in high energy environment, and they existed in the early universe. And the neutrinos of the tau type and the neutrino of the mu type exists all around us. And this was, you will notice here, I have said here nu L, nu M and nu H. So I have not talked about nu E, nu mu and nu tau, because what happens is that what are produced in the sun, for example, are nu E, but what reaches us is a combination of nu E, nu mu and nu tau, because what propagates has a definite mass. Anyway, that's a different subject. I'm not going to spend too much time on that. It's not enough to know what the bricks are. You also need to know how these fundamental constituents are put together, how they're glued together. It's not enough to have Lego pieces, but we have to see how those Lego pieces fit into each other. So what is the mortar? And I already told you that this mortar too, that there are also only 4 fundamental interactions. And I think the biggest achievement of the 20th century has been to understand that not only matter is made up of these fundamental constituents, that these are the only fundamental constituents as we know right now. And actually all our experiments have so far resisted all our attempts to prove that these electrons or the up and the down quarks are not fundamental, that they are made up of something else. We have found no evidence that they are composite. So they have resisted all those attempts. And not only that there are fundamental constituents of matter, that there are only 4 fundamental interactions. For example, Coulomb interaction, effective Coulomb interaction between the electron clouds around atoms provide, for example, molecular forces. So all the interactions that we see are in fact result of some basic fundamental interactions. And these 4 fundamental interactions are mediated by elementary particles. And those elementary particles I already mentioned, were the photon, W minus, W plus and Z0, and the gluon. This was the case till July 4, 2012. But on July 4, 2012, we actually got one more entry to this table, and that was the Higgs boson, and which does not necessarily carry a force, does not take part in mediating these fundamental interactions. It itself has those fundamental interactions, but it provides an interaction which explains why, for example, W plus, W minus and Z0 have this huge mass. Their mass is here 80 times the mass of the proton. And you don't need to worry about this particular unit. You can quote it in any different unit, but roughly this is about 100 times the mass of a proton. All right. So again, the achievement of the 20th century theorists has been to write down, equations of motion for all these fundamental particles. And these equations of motion, for some of you physics students may know, they are obtained by a basic thing called a Lagrangian in classical mechanics. And it is this Lagrangian, a counterpart of that Lagrangian to the world of elementary particles, is what is developed in the last 100 years almost by the theoretical physicists. And right now, it's so compact that it fits on the back of t-shirt, which you can buy in a curio shop at CERN in Geneva. Okay, so all right. So for this theoretical construct to be proved to be true, which was written in 1961, began in 1961, but finally it was completely written down in 1967 by Weinberg and Glashow and Salam. But for this theoretical construct to be proven true, we needed to find the Higgs boson. The stakes were very high, and the Large Hadron Collider was actually built to look for the Higgs boson, which was a spin 0 particle, because there are spin half matter particles, spin 1 force carriers, and the spin 0, which gives masses, or which explains the non-zero masses of all the particles. And this picture I have taken that was presented in the press conference and the first talks of the Higgs boson discovery on July 4th, 2012. And here you see the event where the two proton beams collided with each other, and this is a reconstruction of that event by making correct measurements, complicated measurements by the complicated detector. And what is shown here is the two photons, energetic photons, that were in fact seen by in the detector, and this was sort of the terminus of the train of the Standard Model. And here I like this cartoon, which was published in CERN Courier. It says, we have discovered what nothingness is made up of. And then the other scientist says, yes, it's quite something. So this kind of should tell you what the Higgs discovery meant to the world of particle physics. It was really necessary, so that, this is the term that describes the Higgs particle and its interactions with everything. And this was necessary. These two lines were necessary to make this Lagrangian, from which we get equations of motion for these fundamental particles, to be correct. We needed to be able to write those equations, to be able to prove to ourselves that this is the right theoretical framework. We needed to prove these two lines in this Lagrangian, and one of those was to find the Higgs boson with the right rate that can be produced, and that was something that was done by the Large Hadron Collider. And in 2012, I'm showing you the first observation, and where the Higgs going to two photons was seen as a blip over many other things that happen when two protons collide and produce two photons. And you can calculate at what rate those different processes should be occurring. And then what you see is that at the mass of 125 GeV, lo and behold, you see the signal for the Higgs boson. This is what was seen at that time. And please notice that this is total number of events is 1500. Total number of events here is something like 900. And the Higgs events, as it were, that is the number of events under this red curve here in this small window, is not more than a few hundreds. So why did we believe the Higgs signal when it came at first in just of terms of 100 events? And just to give you a background, there were billions of proton-proton collisions that had to take place for the experimentalist to observe this. So when you have produced only in 100 of the collisions, you have produced these events, why should you believe that you have really found the Standard Model Higgs boson? And this was possible because the signal that was seen by the experimentalist had all the connections with the top quark that we expected the Standard Model Higgs to have. What is meant by that? What is meant by that is that there are two particles that I told you in the table. One is MW and one is MTOP. And these green areas actually indicate the measurements of the masses at different colliders, different experiments. And then what you do is that in the theoretical framework, you have made lots of measurements of properties of lots of fundamental particles that I have listed in the table earlier. And then you make precision measurements of these properties, and then you ask yourself a question. In the Standard Model framework, does it tell me what are the allowed values of MW and MT from those measurements? Sometimes you use the information that you have from MW and MT measurements from the experiments. Sometimes you do not use that information. So this, in fact, these blue ellipses are the ones where you have fitted without using information about MW and MT measurements. So you are actually predicting where the Higgs mass should lie, and then you compare it with the measured mass of the Higgs, what happens in the measured mass. And now what you see is the following. This is the direct measurement of MW and MT. This is the line which you get from the precision measurements indirectly by precision measurements, and then you get actually these fits for assuming different values of the Higgs boson mass. And then you find that the best fit in fact comes when the Higgs boson mass is lying around very close to the known value, the measured value of the Higgs boson. And for the measured value of the Higgs boson mass, the blue circles and the green circles overlap each other completely. So that's telling you that the Higgs boson with the mass of 125.4 GeV that you have seen is indeed the standard model Higgs boson. And that was the reason why even with 100 events, the world went into overdrive and declared we have seen a new boson. Now, where do the predictions for this gray region and this blue region come from? These are measurements, these are predictions from theory. Where do these come from? They come, as I already told you, from precision measurements and precision calculations of the properties of the Z boson. This is what the theorists did. And these precision calculations require us to have the ability to calculate the so-called loop effects in field theory. What does that mean? That means that a Z boson will fluctuate for a very small interval of time into a TT bar pair. This violation of energy momentum conservation will be allowed for a short interval of time. And this small fluctuation can actually modify the properties of the Z boson, its mass, its couplings, and its decay time into different final states. One example is the decay lifetime of the Z into a BB bar quark. And in a good quantum field theory, one knows how to compute these effects in a consistent fashion, and we can have a good quantum field theory only when we have the Higgs boson. What are the lessons we have learned from the plot? There are 3 lessons we learned. We learned that the standard model works spectacularly. But we learned something else. We learned that the space that is allowed for any physics beyond the standard model is very, very small, because this is what the direct measurement of MW and MT tells me. These are what the indirect expectations of MW and MT are. So the space that is allowed for new physics, new interactions, new particles contributing to these corrections is really just the difference, if you wish, between the centers of these green and blue ellipses. And these differences, how statistically significant they are, and so on and so forth, becomes a technical job. And in fact, we know the Higgs mass as well or better as we ever will need for this exercise. So now you can ask the question, what do we need to study further? Why do we need to study further? Now from 2012 to 2019, in fact, the Higgs to gamma gamma events, when we first saw them, as you can see, the total number of events were, the area under the curve of this red curve, and the total number of Higgs to gamma gamma were these few hundred events under this red curve. And now the number has increased, where the number of Higgs to J gamma gamma event has increased 5-fold. It's now 6. The number of events under this area is about 1,000. And indeed, that is because the luminosity, the number of particle collisions, have increased by a factor 7. And indeed, we have collected many more Higgs boson of this variety. We have now collected, this was Higgs going to 2 Zs. In the original signal in 2012, as I told you, there were a handful of events. These are total number of blue events were about 10, whereas now the total number of blue events is hundreds. That is again because the luminosity has gone up by huge factors, and that's what the whole story is about. Actually, we have gone from the discovery to precision measurements. Standard model has very precise predictions how the Higgs boson should couple to the fermions, how the Higgs boson should couple to the gauge bosons, and how the Higgs boson should couple to itself. Now, what we have been able to measure so far is how the Higgs boson should couple to fermions. That is the dotted line is the prediction of the standard model, and the points with error bars are the measurements from the experiments. So again you see that over a wide range of particle masses, the standard model prediction seems to hold true. And now if the couplings were different than this pattern, it would have indicated to us, and it will still indicate to us, that what we have found is not the standard model Higgs boson, or that all the mass that comes that is given to the particles, fundamental particles, all of it doesn't come from a single Higgs boson. Therefore, making more and more accurate predictions of this curve is the next level, the next step. Actually, standard model predictions have been calculated for many processes, and they have agreed with the measurements extremely well. And there are many roads to reach the conclusion of the correctness of the standard model at the Large Hadron Collider. And I just want to show you that this is the production cross section, the rate at which different final states are produced. On the x-axis are a variety of final states. Don't worry if you cannot read it, but what I want to show you, that the different colored blobs are the different measurements. The green, the blue, the red, they are at different energies of the Large Hadron Collider. So one sees actually that the different measurements are consistent with each other. And what the gray things are, okay? But the gray things are, where in here you cannot even see the gray because the gray is insignificant width compared to the actual number of events that are seen. But here the gray is the standard model prediction. And what you see is that over an astonishing range of the rates of processes, because this is at 10 to the 5 picobarns cross section, and this is at 10 to the minus 4 picobarn cross section, and more complexity of the final state, the standard model predictions seem to agree with the measurements, and there is some gap left between the predictions and the measurement, and it is this gap that we would like to explore to see if there is evidence for physics beyond standard model, if there is evidence for an additional Higgs boson, so on and so forth. So actually, after seeing this plot, and for example this plot, or even more importantly this plot, actually you will be justified in asking the question, is there life to particle physicists after the Higgs and the standard model validation at the LHC? And the answer is a resounding yes. And you can ask, are we just saying this because we want to keep our day jobs? And actually the answer is no. And this is the thing that I want to tell you, why there is still life after LHC and the Higgs discovery. Now we need to use the Higgs boson as the tool for future discoveries. And in this case, the theory community, people like us, people like Amit who have joined your department, we have to provide calculations with high precision so that one can use the Higgs boson, the top quark, as a tool for discovery beyond standard model, tool for discovering particles and interactions, some smoking gun signals for these particles and interactions beyond the standard model. Study of theory of strong interaction in a domain where our perturbation theory does not work, and that is lattice QCD, then quark-gluon plasma study at the LHC, and discovery of many new multi-quark bound states that LHC has been throwing up. But third, and last but not the least, is particle physicists have thought about what after Higgs decades ago, even before the Higgs boson was found. And this is called physics beyond standard model. Now, why was this thought about is what I want to tell you. And it produced many big new ideas. But now we have not found any evidence for those big ideas. So are we agonizing over non-discovery of these beautiful theories which we thought must be there but which are not there? And the question therefore can be, is the physics beyond the standard model optional? Is this only a theory's dream, or do we have observational evidence that force us to believe that physics beyond standard model has to exist. And science always progresses in two ways. One way is where pure thought projects you, pure theoretical considerations tell you what is the future path. But there is a second and more important, if not more equally important path, where observations exist which your theory cannot explain. This was like the black body radiation at the end of 1880s or 1890s. And right now, we have many pragmatic reasons, many experimental issues, observational issues that we do not understand in the framework of the standard model. And that is where we have reasons to believe, not where we have very pragmatic reasons which force us to think of physics and interactions and particles beyond the framework of the standard model. And what are those reasons? One is, and you will hear about a lot about that in the second talk, dark matter seems to make 27% of the universe. This got the Physics Nobel Prize in 2019. Then we have direct evidence for the non-zero nuclear neutrino masses. That was the Physics Nobel Prize of 2015. We need to understand why matter dominates the universe. In the beginning of the universe, matter and antimatter was in equal proportions. But now, no matter how far away in the universe we look, we don't find antimatter. Antimatter is dominated by matter. And this is called matter-antimatter asymmetry in the universe. This we don't understand. This has been measured quite accurately. We have found a light Higgs boson at the Large Hadron Collider. That was the Physics Nobel of 2013. We feel the force of gravity, but we do not have a quantum description of gravity. And the cosmic acceleration, which was the Physics Nobel Prize of 2011, implies that there is dark energy, for which also standard model, because it doesn't deal with gravity, hasn't yet had an answer. So this is what this is all about. And there have been a lot of big ideas, as I already told you, and a lot of these big ideas have been proposed in answer to the big questions that the field was asking, and supersymmetry happened to be one of the leading candidates for that. And there were many other ideas. I'm not going to go through that. But supersymmetry, because that's an idea after my own heart, I would tell you, this is the book that Amit had mentioned in his introduction. And this is a symmetry that has been postulated quite some time back on pure theoretical grounds by saying that there is associated with every particle in the standard model, there is a supersymmetric partner which differs in spin by half. And I told you that all the tabular tables had connected together particles with a particular spin. So for all the matter fermions, they are supersymmetric partners with spin 0. For all the gauge bosons, they are supersymmetric partners with spin half. And for it to solve the problems of the standard model, we needed to have partners which have mass such that mass multiplied by c square, it's less than 1,000 times of the mass of the proton. And looking for them at the Large Hadron Collider was one way to probe the BSM ideas. And this is one of the things that were discussed in great detail in this book. The Large Hadron Collider is still probing for the existence of these particles. But right now we seem to think that we have not found any evidence for the obvious ones that could be produced at big rates. And that just says that the masses of these particles, if they exist, have to be bigger, higher than the reach of the Large Hadron Collider. But this theory also has some ready-made dark matter candidate particles, and that might be a second avenue through which the theory can be tested in the current experiments or the future experiments. Actually, theoretically speaking, there are a lot of issues, about how masses get generated. Non-zero masses of the gauge bosons, I told you, they required actually the Higgs mechanism and the spontaneous symmetry breakdown idea, and the same mechanism elegantly also made fermion masses also non-zero, and this was the highly successful standard model. So answering the question about mass generation actually led us to this highly successful standard model. Maybe answering the mass questions the remaining questions about the masses in the universe will lead us to beyond standard model. One is the generation of the invisible mass in the universe, which we picturesquely call the dark matter, which I already said. The second question is, what is the mass of the Higgs boson itself? Why is it light? And one of the ways to keep it light is supersymmetry, for example. And then, however, the masses are generated at the cost of many more parameters in the standard model. And even worse, they span at least 15 orders of magnitude. The neutrino masses are, if at all, they have the mass scale is something like 10 to the minus 19 eV, 10 to the minus 12 eV. And the mass of the top quark is 175 giga electron volts. So it spans about 15 orders of magnitude. We have no real understanding of the hierarchy of the masses. The non-zero, the neutrino masses have actually even more additional facets. And all this means that we have a proof. We have observations which require a theoretical understanding, and those are these issues of what I call mass problems. Now, as I said, we have had many big ideas, and many of these ideas were trying to answer these questions, and those many big ideas indicated that we might find new particles at the scale of 1000 GeV, 1000 times the proton mass, and the Large Hadron Collider results have actually only constrained them. We have no evidence for the beyond standard model Higgs, but we have found the light Higgs, and this light Higgs actually had predicted, for example, this physics beyond standard model. So now the puzzle is, why is it that we have not found this new physics when we have found the light Higgs, which was promised by the property that has been confirmed by observation. And as I said, dark matter, that is the next question. And many of the particle physicists and even the dark matter enthusiasts are beginning to ask the question, does the dark matter have anything to do with particle physics? So somebody like me, who's a particle physicist, who has worked on supersymmetry, right now is working very hard to see whether the observed properties or non-observation of the dark matter actually is consistent with what supersymmetric dark matter predicts. All right. So this is what the story is going on. And the question is then, therefore, are we at a cusp? And some people are beginning to ask the question whether it is time for a paradigm shift, or what is the way forward. An important thing to note here is that if the hypothetical particles that the new ideas are projecting have masses much larger than the energies that are available, then one cannot produce them directly at the Large Hadron Collider. That's what seems to be happening. But they still might leave their footprints on the properties of the known particles like the Z boson or the top quark or the Higgs boson or the B mesons. See, you may not see a tiger, but you will see the footprints after a while, and then you'll say, aha, yesterday night a tiger had passed through here. So that is the thing that we really want to look at now. And this is the one way forward. These precision measurements are going to provide us to a telescope in energy which we can probe. Okay, so one way ahead is indeed through a precision study of the properties of the Higgs boson and the heavy flavor fermions, the top quark, the p quark, that the nature has actually provided us. And that might be one window through which we will get a view of the BSM at present. And this is analyzed in the model independent way, and this is the data driven method. And please remember, standard model itself started its life as an effective theory, which was the Fermi theory of beta decay, explanation of the experimentally observed beta decay in terms of particles that were not known at that time. So it is the measurements and understanding of the properties of the top and the Higgs quark and the B meson. Through this window, we might be able to access the new physics. Till now, the path was very theory driven. And what I mean by theory driven path, I want to go back and show you this. I did not spend the time on the theory of standard model because we are not, we are talking of a slightly different subject. But you see here, This is a theory-driven path. This is the fact that theory gives you precise predictions, and theory tells you where mTOP and mW should lie, and then you find mTOP and mW experimentally in the same region. So this is what is meant by saying that it was a theory-driven path till now. It was the agreement between theory and experiments, or the small differences between the theory and the experiments, that drove us to improve our theoretical ideas, and then drove us to perform experiments to look at properties of the Z boson, properties of the top quark more and more accurately. And that's how the path progressed. Anticipating the scale of BSM physics is a bit like anticipating the Higgs mass in the Standard Model. In the Standard Model, we had predictions for everything, but we had no prediction for the Higgs mass. And it was only the constraints from the other measurements that we could compare with the predictions of the established theory, and then we were convinced that we knew where to look for the Higgs boson, and we found it. So in the old days, there was almost a no-lose theorem. Theory was driving the progress. But now there is one way in which we can still continue, and that is through the mass of the Higgs, because there was no prediction, but we have ideas what constraints it should satisfy theoretically, and those are the constraints through what is very important is that why the whole universe is actually stable over the lifetime of the universe. Believe it or not, that has connections with the mass, what is the mass of the Higgs and what is the mass of the top quark. I cannot go into it, but this is one theoretical direction in which we will still move forward, and in which the measurement of the precision measurements of the couplings would actually play a role. And really the point now is that the days of guaranteed discoveries, which were theory driven in particle physics, are over for the time being. But the big questions of our field remain open. I told you already the big questions. We don't understand the dark matter. We don't understand matter-antimatter and symmetry. We don't understand how neutrino masses are generated. We don't understand why the masses of all the fermions vary over such a wide range. We don't understand how the Higgs boson mass is as small as it can be, because the symmetry ideas actually say that it can be as large as it would like to be, but it is not as large as it would like to be. It is just as large as the mass of the W and the top. And this tells you that now the HGP progress is going to be driven by experimental explorations, and maybe we will have to renounce or review our deeply rooted theoretical biases. And believe it or not, experiments might just have provided us with some indications of where future is going to be. And I want to end my talk with that. This has to do with the fact that normally we say that mu meson or a mu lepton is just a heavier sister of the electron. But some B meson decays seem to indicate that they like to decay into final state containing electrons a bit more than those containing the muon. Now, what is a bit more? That is measured quantitatively, because we are scientists and we have to only ask a question scientifically. And the statement is that over the years, experimentalists actually have measured ratios of many different decay modes. And one particularly interesting decay mode is of a charged B meson, which decays into a K meson and a pair of mu plus and mu minus, and another charged B meson which decays into K plus and a pair of E plus and E minus. And these are experimental details about over which particular energy region you measure these decays. We will not go into that, but this ratio is what is being measured. And just see this. This ratio is being measured over the past almost 7 years. And theoretical prediction is this dash, like this line. Theoretically, we predict this ratio to be 1 plus minus 0.01. This is 1 and this is 1.5. So this is 1.1. So 0.1 is here, right? So that basically the thickness of my line covers the error in the theoretical prediction. So theoretically, you expect this ratio to be 1. Long back, with an experiment called Barber in US, which was measuring B meson decay properties, said that I measure a rate which is quite a bit different from 1, but then there was a big error. And all of you who do experiments we always quote results with an error. And that error really means that there is a, for example, this is a 2, I think this is a 3 sigma error. No, sorry, this would be a 1 sigma error. So this would say that there is a 68% chance that the real answer lies between this region. So if that meant that there was a pretty good chance that number one was the right answer. But as the LHCb, the Large Hadron Collider B, the detector, this is called LHCb, it made its first measurement in the early days of LHCb, and it said, aha, I'm finding an answer which differs from one statistically significantly. And here now you see the measurement is 0.846 plus minus 0.042 plus minus 0.013. So even when it fluctuated to 3 standard deviation, it will barely reach 1, which means that this is a statistically significant deviation from the standard model. And this is now the current result, which has got everybody very excited, because this is a proof that these B decays do not treat the muons and the electrons exactly equally. Theory predicts, the standard model predicts that it should lie here, and what you are finding is that it is significantly different, and there is a 99% chance. This is called 90% confidence level. It's 99% confidence that you can say that this measurement differs from the theoretical prediction of the standard model. Another blip is the magnetic moment of the muon. We are all familiar, engineers, physics students, everybody is familiar with the fact that a wire carrying current produces a magnetic field and a magnetic moment. That is, this current going around in a loop, there is a magnetic moment which is in this direction. Similarly, an electron which is moving and spinning, that corresponds to a magnetic moment, and we are all familiar with this, that the magnetic moment is given by a charge which is charge q of mass m. If it is spinning, gives rise to a magnetic moment which is given by this formula, g times q by 2m into s bar. And we study, for example, in atomic physics, the g factor, the Landé g factor, and the whole story around. For spin half electrons and muons, this g is predicted to be 2, and this is a prediction of theory. Okay, and then the corrections like the loop effects that I already mentioned change the value of g for fundamental particles away from 2. So one of the games has been to measure the g value for a muon very accurately. And what has happened recently, and this is the result of last month, people have measured g minus 2 by 2. This a mu is nothing but g minus 2 by 2. And what you see here is deviation between the standard model prediction of g minus 2 by 2 and the experimental measurement of g minus 2 by 2. And please note, where is the deviation? In the 9th decimal place. So you have to say kudos to the people who can compute the g minus 2 by 2 to 11 decimal places. And you have to give kudos to the experimentalists who have measured it correct to the same decimal places. And then only we have been able to say that this is the standard model prediction. These are 3 standard model predictions. This is the most current one, and this is the measurement. So now again you see this is at 4.1 sigma. This non-zero, this result deviates from the standard model predictions. Now, of course, since standard particle physicists are their worst critics, and because of the immense importance of this big deviation from the theoretical prediction, people are actually once again working very hard to see, is the error in this theoretical prediction believable. In the next 3 years, the error in the experimental measurement is going to go down even further by a factor of 3. So these are the 2 windows. This window and this window seems to be 2 windows where the mu meson properties, the mu properties, are perhaps showing us glimpse of some new physics. Maybe it is there, maybe it is not. On pure theoretical grounds, I bring you the back of another t-shirt. This is a t-shirt that you can buy in the International Abdus Salam Center of Theoretical Physics, and that is the same Lagrangian that I wrote for you, except there is an additional factor of square root of g, and there is this r. This is the gravitation. This is how gravitational will modify that Lagrangian that was discovered at CERN, and this is really the next theory frontier where a lot of theoretical work is going on. And of course, as I said, in all this, in the future, where do we go in future? The experimentalist, apart from studying B meson properties, apart from studying dark matter at the Large Hadron Collider, apart from looking for the footprints in the mu meson, in the properties of the G minus 2 by 2, what is the next direction? The other direction is actually studying Higgs boson as a discovery tool. The first step of the Large Hadron Collider was to find the Higgs boson. We have found the Higgs boson. Now we want to use the Higgs boson as a discovery tool. And when we had actually, theorists had put forward the 4 questions that we wanted to use LHC to study, one was, what principles determine effects of the Higgs boson on other particles? I think we almost know the answer. I've shown you one plot where the couplings of the Higgs boson as a function of the mass of the fermion, and the straight line was the prediction of the standard model, and the measurements were staying on that straight line. So we almost know the answer to this question. We perhaps also almost know answer to this question, is the Higgs really fundamental, or is it composed of more particles? I think we almost know the answer to that question, and that comes from that wonderful plot that I showed you, where MT and MW measured directly agreed very well with the MT and MW that were predicted using the loop precision measurements in the standard model. But I think we still don't have answers to these 2 questions. How does a Higgs interact with neutrinos or with dark matter? And is there one Higgs particle, or are there many Higgs particles? And answers to these questions, we would look not only at the Large Hadron Collider, where we make precision measurements, but we also would like to study this precision measurement of the properties of the Higgs, and logically at a E plus E minus collider, electron-positron collider. Historically, the baton has passed from hadronic, that is for example, LHC is a hadronic machine, a PP collider, and historically the experimental particle physics has moved from hadronic collider to leptonic colliders, and maybe it is the turn of a high energy electron-positron collider. There is one such Higgs factory that is in the planning, and that's the International Linear Collider, ILC. This is one project that is being considered by the community, which might be built in Japan. On the other hand, the CERN community is also investigating another Higgs factory that's called FCC, Future Circular Collider. Instead of making a linear collider, can we make a circular electron-positron collider? And there is a third Higgs factory that is being thought about, that is in China, and that is again circular electron-positron collider, or they like to call it Chinese electron-positron collider. So these are the ideas that are on the board. So now you see there are many different fronts on which particle physics is going to go ahead and discover things. For example, does a Higgs boson interact with neutrinos? Does a Higgs boson interact with dark matter? In fact, a E plus E minus machine might actually be one way in which we can investigate that question. Does a Higgs boson interact with neutrinos? Again, you might need dark matter models to study that. So neutrino experiments are also going to actually provide some information, and the Indian-based Neutrino Observatory, INO, is one effort in that direction. And last but not the least, which is the direction in which I think the subject of particle physics and astrophysics is really merging, and a new subject is being born or has been born over decades now, and that's called astroparticle physics. And my friend Basu would actually tell you some bit about this merging discipline of astroparticle physics. I have already mentioned it to you. I have mentioned it to you that the laws of particle physics that we are studying today in experiments at distant scales of Fermis or less actually have bearing on what happened at the beginning of the universe at 10 to the minus 36 seconds. And here we are now at time scale of 13.8 into the 10 to the 9 years. So what happened so many aeons ago? And LHC, the Large Hadron Collider, is actually trying to probe what happened 10 to the minus 10 seconds from the beginning of the universe, where the energy scale was about 10 to the 2 GeV. And the gravitational wave detections might actually will probe actually what happened here at the 10 to the 16 GeV scales. And no wonder you're going to be listening to talks on these different topics in the afternoon session. So these connections with cosmology, some of these connections can be tested. Some of the theoretical ideas about these connections can be tested by precision measurement at the colliders. And one of them is something that I have been involved over the past God knows how many years. I think I wrote my first paper on the subject in 2007, so 14 years or so. And that is look for a Higgs boson that decays into products which does not leave a track in the detector, the so-called invisible branching ratio of the Higgs. Or the other one I already mentioned, namely that the Higgs mass and the instability of the vacuum may have something to say about the high scale physics and may have connections to some Planck scale physics ideas, to some of these ideas here. So that is a theoretical physicist, particle theorist work does have a bearing on what happens here. So that is the second step. And as I said, gravitational wave experiments will probe physics in this early universe. And I'm very glad that LIGO India is an important part of that exercise. So is GMRT. I don't know how many of you know it, but it's a fantastic meter wave radio telescope near Pune. And the progress now, I think, has to come through joint investigations on the earth and in the sky. One of the things, again, that will be topic of Bala Iyer's talk, is one of the, I think we are in a wonderfully exciting stage where particle physicists and astrophysicists are going to probe the universe through a number of probes. The optical, which is the Hanley telescope in the north of India, the radio telescope, which is GMRT and square kilometer array, gravitational detector, LIGO India, neutrinos, which is Ice Cube, Dune, INO, and also an experiment in China, and the colliders, Large Hadron Colliders, and the ILC. Just to give you one tantalizing glimpse into how you can see the universe in different wavelengths, this is a photograph of the sun through the photons, okay? And this is the same photograph of the same sun through neutrinos. Because the big neutrino detectors in Japan can actually figure out which direction did the neutrinos come from. And then they can actually take a picture, if you wish, of the sun by looking at the angular region in the sky, in the way from where the neutrinos are coming in your detector. So this is the photograph of the sun in the neutrinos. This is the photograph of the sun in the photon. This is one example of multi-probe astronomy. And I think this is going to be really the future of particle physics. And the colliders, the detectors like INO, detectors like SKI and GMRT, detectors like LIGO, and the optical telescopes, all are going to work together in this exploration of what the world physics at the center, heart of the matter is. And it's not just at the heart of the matter, because as we saw, it has implications for the entire universe. So this is the future, and I think the future is extremely bright. Particle physics will now move on to many different fronts: colliders, dark matter detection, neutrino experiments, multi-wavelength astronomy. Path may be very, very long, but it is sure to lead us towards light. Thank you very much.
Thank you so much, Professor Godbole. It was wonderful talk, I must say. With this short time, you have almost covered the entire field of particle physics. And I must say, you have also given us motivations for the next two talks, some glimpse what is supposed to come in the afternoon session. Thank you so much. So it's time now to take some questions from the participants. So maybe I can read some of the questions, and we
Yeah,
also
I
have
saw one question already here. Luckily, I'm able to see the chat.
yeah.
So the
So
one
from
question that I see is, how do we differentiate scalar
Yes.
bosons, vector bosons, and tensor bosons via standard model theory?
yeah,
Now, I don't quite understand what you mean by saying that how do we differentiate via standard model theory, because the point is, when you write a theoretical description of an interaction, you can, the mathematics that you choose for describing the interactions of a scalar boson versus the interactions of a vector boson is different. I mean, mathematics dictates what that for what that description will be, but in the theoretical description. Okay, so I am not sure I quite understand your question. I mean, we are distinguishing them by their spin. Scalar bosons are the ones which have spin 0. Vector bosons are the ones which have spin 1. And tensor bosons, that's gravitons, and you will hear more about it, is spin 2. And for example, when you see the gravitational wave detection, you will actually see there the implications that there are 2 degrees of polarizations. For example, for the spin 1 electromagnetic interaction for photon, for example, how do I know it's a spin 1? I know because the light, electromagnetic waves, has 2 distinct degrees of polarization. When light travels along the z-axis, it can have either the x polarized light or y polarized light. And if I think of circular polarized light, then I will have left circularly polarized light versus right circularly polarized light, and they two correspond to the two cases when the photon has spin parallel to the direction of motion and when the photon has spin anti-parallel to the direction of motion. So it is through observations that I can confirm that what is the spin that a particle has. For example, it is through observations when I look at the decay products of a scalar boson. The decay products of a scalar boson actually are distributed uniformly at all angles. They come out equally at all angles. And for that is what you actually check when you want to check that the spin of the Higgs boson is indeed 0. So I think the theoretical formulation of a spin 0 versus spin 1 is dictated by mathematics, and you check experimentally whether what your mathematics is predicting is found to be true. Am I giving you some answer, Shaunak? If not, then please feel free to repeat your question.
Yeah, so, Sonak, are you there?
In principle, he should be there because he typed it at 11:55.
Yeah.
Can you hear us? Yeah.
So,
Yeah.
does the answers to some extent goes to tell you, because I was not initially sure what exactly you mean by I differentiate via standard model theory, because as I told you, the spin gives me what effects what I would observe in experiments. Spin dictates the effects that you will observe in experiments, and from that you are going to interpret that your hypothesis is correct. For example, why did we say that photon has spin 1? As I said, was because of the 2 degrees of polarization that we observed for the electromagnetic fields. Okay, and that is where we actually also said that the photon must have a mass 0. So what I'm not able to understand, that the theory does not differentiate. The theory, mathematical framework formulae, the mathematics that will describe a scalar particle versus a vector particle is just different. That is dictated by mathematics. Okay.
Yeah.
So
Maybe
do
I
you get
think-
some answer to your question?
Yeah. Thank you.
Okay.
Okay, great. So maybe we'll go to the next question. It says from Ketan. Ketan asks the question, says, how gravity work on smallest scale or micro world?
In the micro world, gravity almost has no implications, right? As we know. Okay. So the gravitational effects or the study of gravitation is really in the macro world. Okay. But when we say that we would like to have a fundamental theory of gravitation in the micro world, a description of the gravity as in terms of, let's say, a graviton, in the quantum description, that is something we still don't have. We still understand gravity only in the classical context. We understand gravitational field in the good old classical context, where there is a center, and the center, the force, there are field lines, and this is the good old Newtonian gravitational description, which is modified by Einstein description of gravity, but which is all still extremely classical. That's all I can say. And what you are asking, that how does it work in the micro world? How does it work along with quantum mechanics? These are the questions that people are asking and working on, and string theory, perhaps quantum gravity would someday answer some of these questions. But for example, one of the things that one studies about black holes have hairs, you have all these words that you might read, that is at the macro world also. The joining of macro world with gravity and quantum mechanics, what has produced very interesting theoretical ideas and paradoxes in the world of black holes also. So gravity actually right now, in my opinion, is the most exciting thing to work on, both in the micro world and at the macro world. Okay?
Okay. So we'll go to the next question from Nitin. He says, does particle size really influence the characteristics of respective materials at considerable order?
Now, this is a very vague question, Nitin, but I am imagining what your question really pertains to is more in the nanoparticle level. There, the size of the particles, as we understand them, does indeed change properties of the materials that we have seen, and that is the particle sizes at nano level. Okay, and that is not something that I have brought here, or that requires a completely different discussion. But indeed, at nanoparticle level, indeed the sizes of the particles do change the properties of the materials, and one can tune the properties of a material by making nanoparticles of certain composition. But the kind of sizes that I had in my mind when I was saying that the electron doesn't have size, I was talking of distance scales which are 10 to the minus 18 meters. So I was talking of not of nanoscales, I was talking of sizes at the 10 to the minus 18 centimeter level. So another 9 orders of magnitude below. So I think without, in some sense your question is very interesting, but it is not exactly about the issues that I was talking about. But what you're talking about is an entirely very interesting subject. And indeed, that's where nanotechnology is developing. And because it is at the nano distance scales, quantum mechanics is required for the study of these particles, and just the ideas of classical mechanics don't work. So that is the importance, where how does particle size influence the characteristics of respective materials. I don't know what is meant by considerable order, but I imagine you want to say at an observable level. And the next question by Sheikh is very simple, that did the Indian government is actually, I think the LIGO India is something that has been sanctioned by Indian government, and you can ask the more questions about it to Professor Iyer, who is one of the persons involved with it from the beginning, and I wouldn't want to take words out of his mouth. And if you, at some stage, Amit, you can even invite the director of NCRA to talk to you about SKA, which is the square kilometer array. And particularly these experiments, and also the high energy physics experiments, are very important because they need cutting edge engineering and cutting edge technology. The thin film technology, for example, or thin membranes, these are the things that high energy physics experiments, or these experiments sometimes require. Material developments, high temperature or high low tensile strengths, all kinds of things. So this is something that is of interest even to big interest to engineers. Okay, so I would say that and right now I think Indian government has supported participation of India at the experiments at the Large Hadron Collider. Indian government had supported even the building of some things for Large Hadron Collider, and that was actually the precision, what are called precision positioning magnets, which are magnets which keep the particle beams, correcting the path of the particle beams. And just to give you an idea how important that job was, the LHC tunnel is 27 kilometers long. A particle is moving at the speed of light along a 27-kilometer path, and you have to keep the magnetic field precise such that it keeps true to its path within a micron. So just imagine that within a micron you want to keep the path of the particle beam correct, because it has to meet the oncoming proton beam. And India actually made some of those precision positioning magnets right here close to Bangalore where I'm sitting. So India has participated in a very important way, and I hope we will continue to participate in these mega projects in a significant way.
Yeah. Okay. So maybe we're running out of time, but at least
Yeah.
we'll take a couple of more questions, maybe, if you permit.
I will take because I feel strongly about the next question.
Yes.
So first I want to
What
admonish
was
Mr.
called
Vivek
God
Narayanan.
particle and
I want to
why?
admonish Mr. Vivek first. At least he should find from himself from the web what was called God particle. At least that question he should not ask me. Okay?
Question is the why.
The question is why, that is different, but he should not, if he doesn't even know what was called God particle, I'm serious about this. I mean, when you are asking questions, don't just ask questions because you are sitting at the back of your chair and let me ask this question. That's not quite appropriate, and I don't think it should be done. I'm sorry, but I would like to tell you this. But anyway, I will tell you what was called God particle. In the newspapers, media, Higgs boson was called the God particle. And therefore, since then, everybody calls it God particle. But frankly, this is just a joke. What happened was Mr. Leon Lederman, who was a Nobel Prize winner and who was the director of Fermilab and very big experiments at Fermilab, he was actually a very good popular writer also. And as I told you, the Higgs boson was postulated by Higgs in 1961, utilized by Weinberg and Salam to construct a model in 1967, and one built a collider in 1984, started building a collider, planning a collider in 1984, and finally one found it in 2012. And till then, all the efforts to find this stupid particle had failed, and all the indirect evidence had mounted. So in fact, when he wrote this book, he had said the title was, according to him, the God damned particle, because we are not finding it. And the publisher said, the public won't take it lightly if you called it damned, so let us call it the God particle. That's all there is to it. There is nothing godlike about this stupid particle. It's the most important particle, of course. It is the most important particle because it completed the theoretical structure. It gave us a clue that the wonderful model that we constructed, theorists, particle physicists, human beings, constructed to describe what happens at the innermost insides of matter, is actually correct. That was the particle that was required to complete the mathematical formulation. It was like the last piece of, that you are trying to build a palace of house of cards, and these were the last two cards that you have to put together and to make the full house. So that is the importance of that particle. But it is nothing godlike. There is nothing godlike about it. It is just a very, very important, it has just a large amount of theoretical importance. So please, I would be very happy if at the end of my 1.5 hour talk, you would stop calling the Higgs boson the God particle. That's all that I have to say here.
Okay. So the next question from Suri Sethi: what is the relationship between time and causality? Is there any relationship? is the time do exist?
I think this question I refuse to
More
answer.
philosophical, maybe.
It's a philosophical question. B, it has nothing to do with what I
Yeah.
have talked about.
Maybe
And
we can take more
I am not going to
topic.
take that
Yeah.
question.
The
Okay?
second, next one is, what is the possibility of Higgs to tau tau? How Higgs is giving mass to a massive particle, also which process has larger possibility to decay from Higgs?
Now, Nivedita, it's clear you have read a few things, so I can tell you this. The Higgs gives masses to all the particles. Now, I mean, contributes masses to all the fundamental particles, not just the tau or the top quark, which has a mass which is about 170 times the mass of the tau, and it gives masses to the W and the Z, which has about 100 times the mass of the tau. So that is not the issue. What I said is that when Higgs gives masses to these different particles, we introduce a extra strength of interaction of a different strength for each particle, and that is the theoretical thing that we don't like very much. Now what you are asking is which process has larger possibility to decay from the Higgs going to WW and Higgs going to ZZ have the WW actually has the largest probability, okay, and Higgs to BB bar. These are the two largest probabilities and final states for the Higgs. But BB bar is not a very easy thing to detect. That's the one that the experimentalists are now going to really focus on. If you look at the plot that I had given, and I'm happy to leave my slides with Amit, you can look at those slides later. If you look at that plot, you will realize that the biggest error in the determination of the couplings with the particles was in the Higgs to tau tau and Higgs to BB bar, because those measurements are very difficult. Though the Higgs decays very promptly into BB bar, we cannot measure it very accurately. But Higgs to tau tau has the advantage that Higgs likes to decay into tau tau at not too small a rate, much bigger rate than Higgs to gamma gamma. And on the other hand, its detection is easier than the Higgs to BB bar. So that is actually the answer to your question. And if you are a student or a whatever at SRM University.
She's from IIT Bhubaneswar, I guess.
IIT Bhubaneswar. Then you can ask questions who are teaching you in IIT Bhubaneswar. There are people who understand these things.
Yeah.
Okay. And
So
Ketan's question is fair enough. Okay. Because he's saying that scientists study dark matter by looking at the effect it has on visible matter. Of course, we can study dark matter particles. That's what we are trying to do. But except that to study dark matter particles, it does not, a dark matter particle, because it does not have electromagnetic interaction, it does not leave a path in the detectors, because all our particle detectors detect energy deposition by a particle through electromagnetic interaction as it passes through the detector. Therefore, looking for a dark matter particle in our collider detectors has to be through what is called a missing energy signal. Okay, and that is the one that colliders do. Then there is direct detection, of which I hope you will hear from the next talk, where you try to see how this invisible particle excite motion in nucleus, and you will measure the recoil motion of so you will study the mechanical effect of a dark matter particle, and the interactions of a dark matter particle with this visible world is what goes into calculating at the beginning of the universe how the dark matter relic density was produced. So that is a theoretical input, and there is something called indirect detection of dark matter, where people try to study recreate the opposite reaction than what happened in the beginning of the universe. They try to see whether annihilation of two dark matter particles will produce a visible particle. So indeed, dark matter is being studied in all these different ways. So I hope, Ketan, you got the answer for your question.
Yeah. So maybe I will take the very last question from Manilal. Can you ask your question? Manilal Amipara. Can you ask your question? We have to close this now very soon. So can you hear me? Manilal? No.
I think his connection is lost.
Yeah, maybe. Yeah, so let's
He can ask the question by email. I will
yeah,
directly answer.
anytime you can email us. We will forward this to Professor Godbole. So thank you, ma'am, and thank you to all the panelists, our VC sir, our dean sir, HOD, and Professor Dasgupta. He will also have to join very soon in the afternoon session. Thank you, everyone. So I have a couple of announcements. Maybe the first one is that we will issue e-certificates, but there is only one constraint, that you have to attend all the 3 sessions. And second is join us at 2 p.m. So we will start the next session, the talk by Professor Basudev Dasgupta, and he will talk about dark matter physics. It will start at 2 p.m. Once again, thank you, ma'am. And
Thank you, Amit, and
Thank
thank you,
you.
Professor V.S. Rao and Professor Narayan Rao, Professor Durga Rao, Dr. Thapar.
Thank you. Thank you very much for your very scintillating, passionate talk. Actually, that's how you live with your passion.
Thanks, Dr. Rao.
Yeah. Thank
You know, that is the only way, I think, the best way to do science.
Yeah, that's what. Yeah,
I think you enjoy it because that's what you love.
that's right.
And
Absolutely.
we don't do it as a chore, but we do it because that's what the mind wants to
That's
do.
what most of us in ISC live with, actually.
Yeah. So thank you very much for your appreciation.
Yeah,
Bye-bye.
thank you.
yeah,
Bye.
thank you. Yeah.